Hi, Dr. Pat here. We're looking at the work problem that I attempted to do in the class. It just didn't work out for me. So let's try it again. All right, what we have here is we have a block. We have 100 feet of rope. We're lifting this block 60 feet. So what we have are three portions to this problem. The first part is the block itself. It's going to move as a whole thing 60 feet up. So we'll figure that out. Then we have the bottom part of the rope. This bottom part of the rope, a section of it, is actually going to move, all of it's going to move 60 feet up. And then we have the top part of the rope where it does not move the same length. So when the very top of the portion basically does not move the full 60 feet of work, because once we get it over that pulley, we don't have any more work of lifting it in the vertical direction. So we have three parts of it: the work on the block, the bottom part of the rope, and then the work on top of the rope. So that's what we got to play with. We're also using the formula for work, which is just force times distance, F times D. And so for us, that's our weight times the distance, our pounds per number of feet that it goes for. So that's what we're doing. So let's take a look at the first one. The first case is the block itself. It's 100 pounds and it's going to be moving 60 feet. So what we basically have is 100 pounds times 60 feet. So 6,000 feet-pounds. So that's the work just on the block to lift it 60 feet. So that's a nice straightforward of it. And then for the next part is we're going to have the bottom portion of the rope. And this whole bottom portion of the rope below 40, another thing, I'm letting x equals 0, my origin, be right here where the rope meets the block. So from 0 to 40 here, this portion of the rope, it will move 60 feet. As a group, as a chunk of rope, it all moves 60 feet. So for that 40 feet of rope, we can just basically do force times distance. And so the key point here is all that part of the rope, the bottom portion of the rope, moves 60 feet. And so since it's 3 pounds per foot, then we have 40 feet of rope. So then what we just do is multiply. So we have 120 pounds of rope. So the bottom section of this rope weighs 120 pounds. It's all moving 60 feet up. And so we just got a nice 120 times 60. So for total work on the bottom part of the rope, I'm using BR there for bottom of the rope, and that's going to be 7,200 feet-pounds. Okay, so that's the bottom part because it's moving up as a chunk, and all of the bottom part is moving 60 feet. No matter what point you take here in the bottom part of the rope, it all moves 60. Now it's the top part. See, the top part is the crazy part. And so what we're going to play with is as we see this rope, one of the things we have to figure out is the distance that each of these pieces of the rope move. And so, for example, I just moved this one piece here that was at x equals 53. So 53 right here, 53 feet up. How far did that piece of rope move to get to the top here? It moved a total distance of 47. So for that one point right here, it moved 47 feet. And so what we have to do is figure out, how did we calculate that 47? What is consistent? Well, each piece right here is going to move a distance. How do we calculate that? How did we get 47? I did 100 minus 53. So the distance for each piece of the rope at the top here, it does not move the same distance. Each piece will move in a calculation of 100 minus x. If I'm towards the top of the rope, I'm going to move a shorter distance. So let's take a look at that. Well, there we go for that one. My graph is doubling. Here we go. So for each top part of this, each piece, that 53 piece, will move that amount of distance. And then this point right here, it actually will move a shorter distance. Okay, because it's already closer to the top, and so it will move a shorter distance. And then that'll move a distance a little bit longer than the previous one. And then that one will move a distance that's different as well. How do I calculate the distance that each of those data points will move? Each point on this graph rope will move 100 minus x will calculate that distance for me. All right, so what we want to do is take each of those data points and we want to find out their distance and then times 3 for the width that we're moving. So each of the distances, those pieces of rope, we're going to figure out the distance, and that distance is already calculated as 100 minus x. I have a 3 in there because the density of the rope is 3 pounds per foot. And then I got a little delta x there because each section of the rope, that represents just a small segment of it. But the key point I want to bring your attention to is we're going to figure out the distance for each point, and we're going to basically add the work for each of those points. Now, if we're adding up the work for each point and we have an infinite number of points on this rope, hopefully you'll realize that what we're playing here is going to be, we're going to integrate. We're going to have an integral here because we're going to be adding very small sections of the rope and doing this movement. So now, which part of the rope are we really working here? Well, it's the 40 to 100 section of the rope. So recall, the first 40 feet, the lower feet, bottom portion of the rope, that all moved a total of 60 feet. All those pieces there. It's the top 60 feet of the rope that each piece on that rope moves a different length, a different distance. And so what part of the rope? It's the 40 to 100 piece of the rope. And so when I'm putting that all together, here's what I've got. I've got my lower bound 40 and my upper bound of 100. This is the section of the rope that I'm concerned about, that I'm calculating. The 40 to 100 piece of the rope. All those that section in between. The density of the rope is 3 pounds per foot, and then 100 minus x represents the distance that each of these sections are moving, and then dx for the little differentials there, the little points on there. Okay, each data point there. And we're talking really microscopic, infinitely small sections of the rope that we're moving. So that's the kind of the theoretical part about that, the dx. Okay, so now I'm ready to do this calculation. My integral's all set up. I've got the bounds. So basically I'm going to take the antiderivative of this thing, plug in 100, then plug in 40, and then take the difference of those two results, and that's where I get 5,400 feet-pounds. And so that's what's going on there. And then when we add all three sections, we get a total work of 18,600. So 18,600 feet-pounds. And so that's the game that we're playing. How to create three different parts to it. How to deal with the block. How to deal with the lower section that as a chunk, all of these points on this rope here, pieces of this rope, section of the rope, all moved 60 feet. It was the top part of the rope that moved different distances to get to the top, and so that's why we had to integrate with this 100 minus x to calculate the different distances that they did. I hope this makes more sense. Talk to you later. See you in class.